In part B of this question, we want to use the second derivative test to see if these stationary points are local minimum or local maximum. And what is the second derivative test? And what is the relationship between a second derivative and a stationary point? Well, let's remember ourselves that if we have a convex shape of a function at a stationary point, that means that the function is literally stationary. It does not have any rate of change, but at the same time it has a convex shape, and that can only happen at a local minimum, at this valley. So that would be a local minimum, where the criteria is that we have a stationary point and an increasing rate of change of the derivative, a convex shape. And what if we have the opposite? What if we reach a point where the function is stationary, but we're reaching it with a flattening slope? Well, in that case, we're increasing at a decreasing rate, and we're reaching a local maximum, where we have again a stationary point, the function does not change, but the rate of change of the derivative is negative. So as we can see, we must know the second order derivative to use this second derivative test. So second order derivative is the first derivative differentiated again. The first derivative was 4x cubed minus 4x, and we're doing it another time, so we're differentiating it once more. What is 4x cubed minus 4x derivative? Well, that's 4 times x cubed derivative, which is 4 times 3x squared minus 4x derivative is just 4. So we have 12x squared minus 4. That's the second order derivative. We have 3 possible stationary points. Let's check what is the shape at those points. So the second order derivative at the point of 0 is equal to 12 times 0 squared minus 4, and that's equal to minus 4. Well, minus 4 is a negative number, and we said that if the second order derivative is negative at a stationary point, then we have a local maximum. So we have a local maximum at the point of 0. That's one point, local max. What happens when we check the second order derivative at the point of minus 1? So second order derivative at the point of minus 1, we're substituting minus 1 into our second order derivative function. So we have 12 times 1 minus 4, that's 8, and that is positive. And if we have a positive second order derivative at a stationary point, we are reaching a local minimum. So this would be a local minimum. And then the last one is, what is the second order derivative at the point of x equals to 1, because that's our last stationary point. Well, that would be 12 times, substitute 1 into x over here, 1 squared minus 4. 12 minus 4 is 8. 8 is again positive. Well, because 8 is positive and it's at a stationary point, we have once more a local minimum. And that's it, our stationary points. We have minus 1 and 1 stays for local minimums, 0 stays for local maximum. We're done here.